Okay, so today I want to talk about elementary topoi, and that's a generalization of a notion of a Grothendieck topos. So, in a sense, we just take a minimal set of axioms to give us something reasonable, and then we'll try to do everything that we do in a Grothendieck topos in an elementary topos. So. Let me just start by listing these axioms. These are due to Lawvere Tierney. And it goes like this. So assume that we have a category, and we say that this category E is an elementary topos if it is finitely complete, Cartesian closed, and most importantly, it has a subobject classifier, meaning that we have a monomorphism from the terminal object to some other object omega, such that for any monomorphism, we have a Cartesian square like this. So basically, any subobject can be obtained by pulling back some kind of universal subobject. That's the idea. And Grothendieck topoi are elementary topoi. It's proved roughly like this. So assume that we have category of sheaves on some site. Then the limits in this category can be computed pointwise. So these are just limits in the category of free sheaves. Since category of sets is both complete and co-complete, limits exist in the category of sheaves. And to take exponentials, we just need to do this. So we have this standard construction of an exponential object in a pre-sheaf category, and then we can extend this definition from, then we just we get another pre-sheaf, and we can show that it is a sheaf. So that's the way to construct the exponential object. And to construct classifying object, subobject classifier, we do the following. So first of all, obviously, category of sets or a category of sheaves on a point is an elementary topos, because there we can just take a singleton set, which is the terminal object in the category of sets. Then we can embed it into two element set, and then any subset pulls back along the characteristic function of this subset. So category of sheaves has a subobject classifier. And now we can just extend this idea to any topos using the following construction. So assume that we have an object U on our site. Then we define the value of this pre-sheaf on U as just it's just the set of all sub-sheaves of the representable sheaf which corresponds to U. So we assume that our topology is subcanonical, meaning that all representable pre-sheaves are sheaves. And then we say that the value on an object on our site should be just the set of all sub-sheaves of the representable sheaf which corresponds to U. And then basically by default, we get that a sheaf defined this way. First of all, a pre-sheaf defined this way, first of all, it is a sheaf. And second, it is a subobject classifier for an arbitrary pre-sheaf. For an arbitrary sheaf, because we can extend by co-continuity. So any sheaf is representable as a co-limit of representables, and we can use that to show that omega defined in this way gives us the desired subobject classifier. So a construction works roughly like this. And obviously, the morphism from the terminal object into omega is given by, well, on U, it is given just by taking U into omega U, where U corresponds to subsheaf, to the identity subsheaf of YU. So, okay. So still one point, and this 1 point precisely corresponds to U, or even more precisely YU, which is a subsheaf of YU, obviously. Okay, so let's consider an example of all this. So first of all, recall that last time we discussed locale topology, and in particular, if we have a locale, then we can take its frame, and as we said last time, it carries a canonical topology, which is an analog of open cover topology on topological spaces. So a family is covered, and if and only if a join of this family coincides with the thing that we try to cover. Then we can define a category of sheaves on this locale by taking as a site the frame of this locale, and as topology or coverage, precisely the collection of all these covered families. Then this category consists of three sheaves such that their value on an element of this frame, on an object of this frame, coincides with an equalizer like this. So we just take product of values on elements of the covering family, then we and then we co-equalize it with products over pairwise meets of elements of this family. So that's a very standard definition of a sheaf basically on topological space. So how do we construct the subobject classifier in the category of sheaves on the locale? We do it like this. So for an open subset or for a representable sheaf, we take the value of omega on U to be just the set of all objects in the over category of U. So basically just all open subsets of U, or open subsets of X contained in U. And we can explicitly show that omega is a sheaf. How we do that? Well, first of all, it is clear that we have a fork like this, because obviously if we have an open subset of U, then it can be represented as an element in such a product, because, well, if it is an open subset of U, then it is equal to meet of W and U, which is equal to this meet, which by the distributivity is equal to this thing, and this thing clearly defines an element in such a product. So why is it an equalizer? Well, we need to show that well, open subsets, so to speak, of U precisely correspond to elements in such a product that have the same image under both of these maps in this product of sets of open subsets of pairwise meets in this covering family. And obviously we have a representation of W like this, so we can So we can subdivide each UI into pairwise meets. They obviously still form a covariant family, and we have this equality. Then let's try to understand when a collection of open subsets in each UI defines an open subset in U. Well, as it turns out, precisely when after restriction to pairwise meets, we obtain the same thing. So obviously, if we have such a collection, then we can take a meet of this collection, but the problem is that we can take meets of two different collections and yet obtain the same open subset, in U. So to illustrate, consider on one hand collection which consists of a pink subset and a blue one, and on the other hand consider a collection which consists just of a pink subset and an empty set. Obviously, they are different as an elements of the product, so they're different here. But in the end, they give us the same subset in U. So we need to somehow rectify this, and for this we consider this equalizer. So this equalizer takes care of possibility that two different families give us the same subset in U. And that's basically the idea of why this pre-sheaf that we define for an arbitrary Grothendieck topos is actually why this pre-sheaf is actually a sheaf. So it works roughly like this. Well, I mean, I explained it only for this particular example, but the idea is quite similar. Okay. But it's important to note that there is a difference between Grothendieck topoi and elementary topoi. So there are examples of elementary topoi which are not Grothendieck topoi. And basically, in some sense, this example is not very interesting, but nevertheless, we can consider a category of finite sets. And then it is not a Grothendieck topos for a very stupid reason. It does not have enough limits and colimits, because obviously if we take a Grothendieck topos, it should be closed under arbitrary limits and colimits, because the category of pre-sheaves or sheaves is closed under such. And similarly, if we take pre-sheaves or sheaves on an arbitrary category valued in finite sets, we will once again obtain a category which is an elementary topos, but not a Grothendieck topos. So for the same stupid reason, we don't have enough limits and colimits. And I guess a noteworthy example of this construction is a category of pre-sheaves of finite sets on one object category corresponding to some group. So this thing forms an elementary topos, but not a Grothendieck topos. Okay. So now let's discuss the notion of morphism between elementary topoi. So a geometric morphism between elementary topoi is a pair of adjoint factors like this. So we have a right adjoint, which corresponds to the direction of our geometric morphism, and a left adjoint, which goes in the opposite direction. So this is called a direct image functor, And this is called an inverse image functor. And in a moment, I will relate it to what we discussed last time about what kind of topology. So a natural transformation between geometric morphisms is a natural transformation between direct image functors, which naturally corresponds to a transformation between inverse image functors by adjunction. Okay, so this picture should be quite clear if you saw any operations with sheaves on topological spaces. Then there we usually have two functors as well. Well, these two functors which always exist and are easy to describe. So yeah, before I'll go into some examples. So let me just formulate another enhancement of this definition. So a morphism between topoi, a geometric morphism between elementary topoi is called essential if, in addition to these two adjoints, we have also a left adjoint to the inverse image functor. So we have this f shriek, which is a left adjoint to f upper star. Okay. So if we have a morphism of localities, then we have an adjoint pair which corresponds to a geometric morphism of topoi, and it works like this. So for the direct image functor, we just take a precomposition of f. So if f is a sheaf on X, then we just need to take a precomposition with f inverse, where f inverse is the corresponding morphism of frames. So f inverse goes in the opposite direction, and it becomes a morphism of frames, just by the formal duality between frames and localities. And for direct image functor, we just need to, for inverse image functor on sheaves, we need to apply the direct image functor on frames, which was described last time, and the definition was that we take all elements of the frame of Y such that f inverse of them is a subset, well, an open subset of U, and then we take a join of all such elements. So we try to approximate U by approximate U from below by elements of the frame corresponding to Y, and that's the direct image on direct image functor on frames, which is not necessarily a morphism of frames, as we remember, but nevertheless it is sufficient to define a new sheaf which comes from a sheaf on Y. So we take as an input a sheaf on Y. We apply this direct image of open subsets, and we obtain a sheaf on X. Okay. So another example is just something that is slightly more general than this previous example with frames, namely that we can take a site, and then we can take a category of sheaves on, well, I mean, this particular example is not, I'm sorry, it's not a generalization of the previous one. I was thinking of something else. This is just an example that we can have a morphism from arbitrary Grothendieck topos, which is a category of sheaves on this site, into the category of pre-sheaves on the same site, or equivalently sheaves with minimal topology. And this inclusion defines a geometric morphism where one direction is just the inclusion and the other is the sheafification functor. So this is also a geometric morphism of topoi. I guess an example that I was thinking of was something called a morphism of sites, or a continuous morphism of sites. Let me just a moment. Let me just briefly say something about that, because somehow I forgot to put this example here. A continuous morphism of sites is obviously a functor. So we have two sites, Cj and dk. So we obviously should have a functor between C and D, and it should be such a functor that if we consider that if we consider a covering family on the side D, then it can be lifted to a covering family on the side C. So what does it mean? Well, let me write this down 1 moment. Okay, so assume that we have a covering family like this. So we have a covering family, let's not compare, of an object Fa. So A is some object in C, and we should have a cover of this object in the category C. Such that it is compatible with the cover B. So what does it mean? Well, it means that we should have for each J, we should have commutative diagrams like this. So for each J, there exists an I such that the map from the value of F on this map from this covering factors through some other covering map from another covering on F of A. So that's the notion of a continuous morphism. And if we have continuous morphism of sites, then we have a geometric morphism of sheaf topoi. So it's not completely obvious, but if you think of it a bit, it becomes more or less clear, because this condition precisely ensures that sheaves go to sheaves. So since sheaves are precisely local objects with respect to, well, in case of arbitrary sites, I guess with respect to hypercover descent, but in general, but in some particular cases where we have a classical notion of Grothendieck topology just with respect to the usual well, they should be local with respect to the usual maps from truncated Czech complex to a representable pre-sheaf. So this condition,
sorry.
yeah.
Sorry, could you repeat this definition?
Yeah, I mean, it's just a fancy way of saying the usual descent conditions. So when I say truncated check complex, it just means that we can consider we can consider a covering, right? And then we can associate to it a check complex. So if this is a covering, then we can associate to it a check complex, which is just delooping of a groupoid, which corresponds to one moment, maybe. One moment. Delooping of a groupoid, which corresponds to
I mean the definition of morphism between sides.
Oh, okay. Sorry. Yeah. Yeah, I didn't understand you. The definition. Okay. Yeah. So let's forget about this for a moment. Yeah, the definition of morphisms of sites once again is like this. So we have a functor between the underlying categories, right? And then we require for an arbitrary object A. So for an arbitrary object A. And an arbitrary covering family, consisting of BIs in the category D, so it should belong to K of F of A. We require existence of a covering family on A inside of a category C, such that for any index J, the map from FAJ to FA factors through some BI from this covering.
Okay, thank you.
Yeah, right. So then we can forget about this stupid explanation of why it induces a morphism of sheaf categories. But the idea was that this condition is sufficient to preserve the class that we localize in, which means that it preserves the subcategory of local objects, which means that we have a morphism between sheaf categories. So the adjunction, obviously, if we have such a functor, then we have an adjunction between pre-sheaf categories because minimal topology is trivially preserved. And what we need is to push this adjunction down to the subcategory of local objects. And essentially, precisely this condition allows us to do. Okay. So let's return back to these examples. So assume that we have two elementary topoi, then we can form a product topos, and we have two projections. So I state the following. We have a geometric morphism which corresponds to a projection on.
Hide the left panel, please.
Okay. Okay. Thank you. Yeah, so we have a geometric morphism of topoi which corresponds to a projection. So it's a certain not very hard statement that the product of two topoi is actually a topos itself. So this is a geometric morphism where the right adjoint is given by the projection and the left adjoint is given by a product with the initial object. So since our topoi are finitely complete. They, well, for other reasons too, they have the initial object and basically a projection admits a section, and therefore we have a left adjoint. And additionally, if the other topos has an initial object, then the projection is essential and left adjoint to the product with the terminal object is the product with the initial object. And as we will see, this if assumption can actually be dropped, because although our axioms of a topos were not self-dual, meaning that we didn't require existence of finite colimits, actually, as we will see, finite colimits exist as well if we require existence of finite limits. But more on that later.
So you have described the product structure, yeah, in this case.
What do you mean describe the product structure?
Cartesian products, I mean, or I don't understand. The letter passage was about what? Sorry.
So this part was about the fact that if this part was about the fact that if the topos say if we consider P1, then if E2 has so if we consider P1, then if E2 has an initial object which is denoted by 0, then Pi, I mean P1 in this case, is essential. So what is an essential geometric morphism? Essential means that the left adjoint has a left adjoint. So we have this F shriek. And this means that, well, in this case, we can construct such a left adjoint by taking multiplication with the initial object. So it will, one moment, maybe I'm saying something stupid. Yeah, probably. Yeah, saying something really dumb here. One moment. I'm sorry. That's not what I wanted to say because it doesn't make sense. Should be an adjoint to the projection, not to the section. One moment. Yeah, so yeah, right. What I wanted to say was that actually, yeah, we have a left adjoint to okay, I see. Yeah, so yeah, I want yeah. Okay, so the correct order is reversed. So the correct statement should be like this. So we have a morphism from E1 to okay, so Pi is the inverse image, and the direct image is given by multiplication with the terminal object. And this F shriek will be given by multiplication with the initial object. So looks like this. So we have, this means that we have a morphism from EI to E1 times E2. And then we have two morphisms in the opposite direction. Oh no, okay, once again, I've done something stupid. We have two morphisms like this, and we have one morphism like this. So one is given by multiplication by initial object, one is given by multiplication by the terminal object, and the map in the middle is the projection. Yeah. So this is correct. Okay. So sorry for this confusion. All right. So this is an essential map, an essential morphism, as we will see later. Okay. So now another useful thing about topoi is that they more or less behave like the category of sets. For example, we have the following nice property of this category, that if we have a monomorphism in this elementary topos E, then we can represent it as an equalizer of a pair of morphisms. So obviously, for example, in sets, this always works. But actually, we don't need, we don't need the set structure to do this. So in sets it works basically like this. So if we have a subobject in Y, then it is represented as the pre-image of a point in the, well, we have a morphism from Y to the quotient set, and then well, this morphism equalizes the projection and the morphism that factors through a point, for example. So this is a way to see this in sets, but actually a pretty similar argument works in an arbitrary elementary topos, and it goes like this. So assume that we have this universal monomorphism, then it can be represented as an equalizer of two morphisms like this. So we have the identity morphism on omega, and we have a morphism that factors through the terminal object. So this is the canonical morphism, and this is the morphism T. Then for an arbitrary monomorphism, we can show that it is an equalizer of a pair of morphisms like this. So we take the identity on Y, and we take the morphism that factors through the terminal object. So basically, we just pull back this diagram for the universal monomorphism to an arbitrary monomorphism. And this shows that any monomorphism in a topos is an equalizer. Okay. So this seemingly trivial result implies that in a topos, we have a familiar property that any morphism which is both an ectomorphism and a monomorphism is actually an isomorphism. So how we do that? Well, assume that we have an equalizer like this, and it is additionally an ectomorphism. This means that, first of all, well, it is a fork. So we have this. But actually, since it is an epimorphism, we can cancel F. We get that G is equal to H. And this means that F is actually isomorphic to the identity map on Y, because the identity map is also an equalizer of such a diagram. And by the universal property of the equalizer, F should be isomorphic to the identity. So I guess this is a demonstration of the fact that we actually need very little from the category of sets to get many familiar properties of this category. Okay. So now let's discuss equivalence relations in topoi. So first of all, what is an equivalence relation in a category? Well, basically, we just need to categorify the usual axioms of an equivalence relation. So an equivalence relation is a pair of morphisms from an object to another object, such that first, it is well, if we take a product of these two morphisms, we get a subobject in a product of this object. Second, in a sense, I guess you can drop this assumption and just say that you get an arbitrary morphism into the Cartesian square of your object, but then your equivalence relation will be sort of redundant. So you'll get some information that is unrelated to X. So you get well, I mean, if you work in sets, then obviously you can add to your equivalence relations some unrelated information that does not say anything about elements of X, but I mean, that's just pointless. So this is sort of a technical requirement for an equivalence relation. But then there are three familiar axioms of an equivalence relation. So the first one is an axiom of reflexivity. So this just says that the diagonal map should factor through R. So in sets, that would mean that all pairs of the form x small from X belong to our equivalence relation. The second one says that the relation is symmetric, meaning that we should have a transformation on R, so an automorphism of R, or at least an endomorphism, such that B tau is equal to A and A tau is equal to B. So this is the categorification of the symmetry property of an equivalence relation. And finally, we should have the transitivity axiom, which categorically can be stated like this. So define T to be a pullback in a diagram like this. So we have the first projection of an equivalence relation, the second projection, and we just take a pullback. And then the map from T to the product given by compositions in a wrong order, so to speak, should factor through R. And that basically means that if we have alpha equivalent to beta and beta equivalent to gamma, then alpha is equivalent to gamma. So this T is basically the collection of triples like this, and then when we take such a map, we just sort of forget about the one in the middle. So then we require that such a map factors through R, and that's a categorified version of the usual definition of an equivalence relation. Okay, so an equivalence relation is called effective if it can be presented in this form. So we have one morphism from X to Y, such that the equivalence relation can be constructed as a pullback like this. So this pair is called the kernel pair for F, and the converse is true, that if we have an arbitrary morphism from X to Y, then if we form a pullback like this, then it automatically becomes an equivalence relation. So, yeah. Yeah. No, I don't think that we want to say anything else. Yeah, okay. So that's the definition of an effective...
Sorry. Sorry, in the first diagram, we have any F. Yes.
Yeah. Yeah.
For any F, we should have this diagram, and where A and B from the definition of the equivalent relation. Okay.
Yeah. Yeah, I mean, for sets, that's kind of obvious because, maybe I'll say something stupid here, but well, let me try to just very quickly to reconstruct why any equivalence relation in sets is effective. So assume that we have an equivalence relation, then R is just a subset in this product, and I guess let me think. What should be the... Yeah. I guess I'm pretty stupid. Yeah, we just need to take the quotient by this equivalence relation. Yeah. And then we'll get this thing here, and you can see that this is actually both a Cartesian and co-Cartesian diagram. So yeah. And we have obviously we have the same projection map here, and as you can see, for sets, for obvious reasons, this is also a pullback square, and so any equivalence relation in sets is effective. Yeah. Okay. So let's try to do. Yeah. Sure. Thank you for the question. Yeah, so let's try to do something similar in arbitrary topos. So in arbitrary topos, the same thing holds, and we basically can show that any equivalence relation is effective. I will give the construction for this, which is somewhat similar to the previous one. So assume that we have an equivalence relation R to X. Then we can take a pullback square, which looks like this. So we have the universal monomorphism. We have the map which classifies the subobject R. And then we can show that actually R is an equalizer of this pair, so R fits into a diagram like this. This pullback square. I mean, it's not very hard to verify that under this definition we obtain precisely this equivalence relation. Okay. So now let's discuss something a bit different. That's partial maps. So partial map is basically the same thing as a partial function in sets, well, in this case, maybe it's better to call it partial morphisms and partial maps and sets, whatever. So what is a partial morphism? Partial morphism is a diagram like this. So we have a subobject in an object X, and on it we have an honest morphism to Y. And then we call such a thing a partial map from X to Y. So as the name suggests, it's not defined on the whole object. It's defined only on some subobject. Then we say that partial maps with codomain Y are representable if there exists an eta from Y to Y tilde, such that for any partial map from X to Y, we actually can, one moment, I think that there should be not a push out square, but a pullback square. Let me check this. Yeah. So we have a unique F tilde making this diagram a pullback square. So that's the definition of a representable family of maps. So or I don't know, maybe it's more appropriate to say it a representable object, because we say that, I mean, all partial maps into Y can be presented like this. And if Y is equal to the terminal object, then this becomes just the axiom of existence of a subobject classifier, because partial maps into the terminal object just correspond to subobjects, and this is precisely the requirement that all subobjects can be obtained as pullbacks of a universal subobject. But as it turns out, and that's called the Lawvere Tierney's theorem, it's actually unimportant if we're considering Y equal to 1, or if we're considering an arbitrary Y. Actually, for any Y, the maps into Y, the partial maps into Y are representable. So all maps in a topos are representable. And let me once again sketch a construction of such a representation. But first of all, let's define the following monomorphism from an arbitrary object into this exponential object. This should be thought of as an object of subobjects. So in sets, so that will be the set of subsets. Because in sets, omega is equal to 2-element set, and this will be just the Boolean of our set. And then we have this singleton relation, which is just in sets. It's just an embedding of a set into the set of all its subsets, given by taking each element of the set into the corresponding singleton subset. So we have a monomorphism like this, but obviously for an abstract topos, we don't have any elements, and we can't say that we embed our object via singleton subsets, but we can abstractly do this by considering the following. So we have a diagonal subobject of the product, then it can be classified by some map delta, and then to delta we have a corresponding map from X to omega X. Well, it corresponds by the universal property of an exponential object. And this is a monomorphism because this map actually is an equalizer of a morphism from one moment. Yeah, because this map fits into the following pullback square. So we have a pullback square where here we have identity maps, and the other two maps are precisely these singleton maps, which shows that they're actually monomorphisms. So that's one part of our construction. Now let's show that any morphism in the topos is representable. To do this, consider an arbitrary object of our topos and consider a composite like this. So we have a map from y to the product of omega to the power of y and y, which works like this. Then we have a classifying map from this for this subobject we denoted by phi. And then we can consider an adjoint map. So we use the exponential adjunction to get a map from power object of y into power object of y. Yeah. So then y tilde, so this ambient object of y is constructed like this. We just take the equalizer of phi bar and the identity map, and we obtain this subobject. And then it is not very hard to show that after such construction we obtain precisely what we needed to. So this ambient object which classifies all partial maps into y. Yeah. Okay. So in particular, this construction of y tilde shows that any topos has sufficiently many injectives. So what is an abstract injective object? Well, we just say that an object is injective if for any monomorphism like this, well, basically if for any partial map there exists a lift like this. So it is quite reminiscent of the notion of injective module, injective abelian group, which is a particular example, but whatever. So consider as this injective envelope this object y tilde that we constructed earlier. So assume that we have a partial map like this. We want to show that there exists a lift from x to y tilde. To do this, we first consider the following pullback. So we have a monomorphism from y to y tilde. We have a morphism from x prime to y tilde. Then x2 primes is the pullback of one map along the other. So then x2 bars is also a subobject of x, because when we pull back a monomorphism, we get a monomorphism. And also we have a partial map from x prime to y. So we can sort of flip this diagram, and then it will look exactly like a diagram of partial map. But this means that there exists a unique map from X to Y tilde that classifies this partial map. Well, okay. But this means that we actually constructed this lift because we wanted to map from X to Y tilde, and we got it. It's precisely the map that classifies this partial map from from X prime to Y. Well, actually from X to Y, because if we have a partial map from X prime to Y, that means that we have a partial map from X to Y, because X prime is a subobject of X. So, I mean, to be completely rigorous, we need to actually show that this triangle commutes, but this follows from the fact that this map actually one moment. This follows from the fact that actually, if we consider the partial map, which is defined. Okay, so we have a partial map from X prime to Y, and this morphism also classifies this partial map from X prime to Y. So this shows that the triangle commutes. Okay. So we have this result that any object in the topos can be embedded into an injective object. And now let's move on to the final big part of my today's talk. That topos axioms are actually self-dual. So we formulated them in not quite a dual way, stating that only finite limits exist and not colimits. But as we will see, actually finite colimits also exist. And even better, we will describe the opposite category of an arbitrary elementary topos as a category of algebras over certain monad in the topos itself. So as a first idea of how this works, we have the following easy exercise from category theory, stating that the opposite category of sets is concrete. How we achieve this? Well, we can consider a functor from the opposite category of sets into sets, which takes a set into its power set. Then obviously on morphisms, we have the pre-image of a subset, which gives us the morphisms in the opposite direction. So in a sense, for category of sets, if we only knew that we have only if we only knew that we have limits in sets, this result will immediately show that we also have colimits in sets. But this rough idea can be extended to an arbitrary topos, although by using not so elementary methods. And so I will try to explain how this works. Okay, so first of all, we can consider a category of topoi, actually two categories of topoi, where morphisms are geometric morphisms and two morphisms are given by natural transformations between geometric morphisms. And for an arbitrary topos, we have a functor which from the opposite category of this topos into the topos itself, which works precisely like in the case of sets. So we just map X into its power object. That's what P stands for, power object. And the morphism is mapped into a morphism in the opposite direction, which is constructed like this. So we have a map from omega y times x into omega y times y, which is given by this product. Then we have an evaluation, which is a map from omega times the power object of y times y into omega, which evaluates a morphism from y to omega on y. And then we can use the exponential adjunction to obtain a morphism from omega y into omega x. And we also have a functor in the opposite direction, which goes from E to E op. And it is the same functor, but we consider it formally as a functor from the category to the opposite category. So the data is precisely the same, but we just formally dualize the image, which allows us to define such a functor. Okay. So now we have the following lemma. So this pair is a pair of adjoint functors. And also another important fact is that if we have a monomorphism, then we can actually define a map between power objects in the different directions. So it is sort of covariant. So it's a map from omega x to omega y, which is defined like this. So we take a subobject of this product omega x times x, classified by the evaluation map. So this is this belongs to x kind of subobject. And then we also have a morphism like this. So then what remains is to one moment. So we define moment. So we define a composite like this, and then we can take moment. We have a monomorphism like this. One moment, I'm sorry. So we're supposed to take the transpose of morphism like this. Maybe I just don't.
Sorry, epsilon sub x. What does it mean?
It's a subobject which is constructed, which is classified by the evaluation map. So this constructed as a subobject, which is a pullback along the evaluation map. Yeah, I just sorry, I just don't understand how we obtain a map from omega x to omega y. So we have a map like this. Have a map like this.
It seems that we should have the map in opposite direction.
No. Let me explain. So in sets, this works very easily. If we have a subset in X and we have a monomorphism, then it automatically becomes a subset in Y. So we actually have a map in this direction. That's the point. So if we have a monomorphism, then we should have now I see. Yeah, that was okay. One moment, let me add the page and I'll explain what's happening. Yeah, it was just a bad preparation. Okay, so first of all, let's fix what we know. So we have this subobject, which is pulled back along the evaluation map, right? Then this thing can be interpreted as a subobject not in omega x times x, but actually in omega x times y, because, well, you saw that we had this monomorphism from here to here, and the composition of monomorphisms still monomorphism. Okay, then we can try to classify this. So we take a map which classifies this subobject. And then, well, I don't know. Let's call it what we should call it. Well, I don't know what we should call it, but let's call it psi. Then we can use the exponential adjunction to obtain a map from omega x to omega y, which is called exists F. Yeah, that's the construction. I'm sorry.
Cool.
Yeah. Is it understandable, clear? I don't know.
Yeah, it's cool.
Okay, great. So in sets, that should just correspond to the fact that if we have an injection, then each subset of the domain is also becomes a subset of the codomain. I mean, in sets, it's somewhat it's not that intuitive. Why we should even bother? Because for sets we can always define a map in the different direction by just taking the image of a subset. But for this construction, it has some good functoriality properties, and also it works in an arbitrary topos and not just in sets, which is quite important. Okay. So let's formulate another well, easy lemma called Beck's condition. So assume that we have a square like this. So a pullback square where two maps are monomorphisms. Well, actually, we need only one map to be a monomorphism. Then, if we apply the functor omega and replace the vertical arrows by these exists arrows, which we constructed in the previous slide, we will get a commutative diagram. So that's just a lemma, and it has a cool corollary to this. We have a cool corollary to this lemma that says that if we have a monomorphism, then if we take a composition of PF and exists F, then we get the identity map on omega X. So in a sense, that's, well, once again, if we use our set theoretic intuition, that's quite clear, because if we have an injection, then we take the image of any subset, we obtain a subset, then we take the pre-image and we obtain the same subset. That's basically a condition that can be taken as a definition of an injection. But once again, abstractly, it's not that clear, but it immediately follows from Beck's condition. So we just need to take a square like this. So it's a pullback square because F is an injection. And after we apply omega, we get a square like this. So two sides of the square flip, because on the bottom and on the top, we use the contravariant, the contravariant maps. And we get, a map from omega x to omega x, and a map from omega y to omega x. So the sides flipped. But here, nothing flips because we use this covariant construction. And here we get exists F, here we get PF, and here we get the identity maps. And so Beck's condition shows that by commutativity, the composition of PF and exists F is the identity map. Okay, so now to show that an opposite category of a topos is actually a category of algebras over a certain monad in this topos, we will need a categorical gadget called Beck's monadicity theorem. And first of all, just some recollections about adjunctions and monads. So assume that we have an adjunction, and then we have a unit, a co-unit, and we can define a monad as follows. So a monad on the category C. So we take the functor T to be the composite of F and Q, and we take the multiplication of the monad to be this natural transformation. So TT is just UF. We use the co-unit to get rid of FU in the middle, and we obtain a natural transformation into UF, which is T. So that's how multiplication works. And eta, as the name suggests, is just the unit of this adjunction. So we have this, well-known construction of a monad from an adjunction. Then formulate Beck's monadicity theorem, we also need the following notion. So assume that we have a functor from D to C, and we have a pair of morphisms. It is called U-split if we have a co-equalizer of UA to UB called H. Called H. And there are sections S of H and T of UF such that the following compositions are the same. Okay. So that's all well and good. Then we say that U creates co-equalizers of U-split pairs if for any U-split pair there exists a co-equalizer in D. So not just in C, but in D. So this initial pair also should have a co-equalizer. And moreover, this co-equalizer is preserved by U. But not only that. So for any fork is a diagram of this form. Computer diagram of this form. So for any fork, if we apply U and get a co-equalizer, then it was a co-equalizer from the beginning. And finally, we say that a co-equalizer is reflexive if there is a common section. So a co-equalizer, something like this, and we say that, well, I'm not sure that we even need a co-equalizer, but just say that a pair of morphisms is reflexive if there is a common section of this pair. So we have NS such that Fs is equal to GS is equal to identity only. Then additionally, we'll need the following ingredients. So assume that we have a monad on a category, then we'll denote by CT category of T algebras. And for injunction and the monad T defined as before, we have the following comparison functor. So it goes from the image of the left adjoint, the codomain of the left adjoint, into the domain, or well, into the category of algebras on the domain of the left adjoint. So the definition of this functor is like this. So we map an object M in D into UM, and the well, sort of I forgot the proper name, but the action morphism of this object is the value of U on the co-unit of this adjunction. So UEM is a transformation, well, is a morphism from TUM into UM. So UM becomes an algebra over T this way. So if we expand T, we get that well, FFU is annihilated by EM, and we get a morphism into UM. So an injunction is monadic if K is an equivalence of categories. So the content of Beck's monadicity theorem is a necessary and sufficient condition on an injunction being monadic. So yeah, the theorem states the following. It is the precise, so-called precise monadicity theorem. That if we have a functor from D to C, then it is monadic if it has a left adjoint, and it creates co-equalizers of U-split pairs. This theorem has corollary, which we'll actually use. It is called crude monadicity theorem. And there are two benefits to this formulation. So the first benefit is that it is somewhat easier to check. And the second benefit is that although the conditions of the crude monadicity theorem are not necessary, so there are monadic adjunctions which are not, which do not satisfy conditions of crude monadicity theorem. The composite of monadic adjunctions which satisfy the conditions of crude monadicity is also a monadic adjunction, which is not true for arbitrary monadic adjunctions. So if someone recalls what we had last semester about deformable adjunctions, this is similar, because because it is in general not true that a composite of deformable adjunctions is deformable, but for example, for Quillen functors, it is true. So in a sense, we have an adjunction which preserves a certain structure which is needed for the next adjunction to be once again monadic. So let me state the crude monadicity theorem. It is basically very similar, but instead of taking U-split pairs, we take reflexive pairs. So reflexive is slightly stronger than being U-split. So a functor from D to C is monadic if it preserves isomorphisms, has a left adjoint, and it preserves coequalizers of reflexive pairs. And then under these conditions, well, the functor is monadic, the adjunction is monadic. So this categorical gadget allows us to prove something known as Perez theorem, and it states the following. So the functor of the polar object is monadic. So the category of the opposite category of a topos is actually a category of algebras over the monad which corresponds to the adjunction P lower star P. And the proof goes like this. So we want to show that we have this equivalence constructed by a comparison map, which goes from comparison functor, which goes from the opposite category of E into category of T algebras in E. And we'll use the crude monadicity theorem to show that this comparison functor is an equivalence. So it is enough to show that P preserves coequalizers of reflexive pairs and say that it preserves the isomorphisms. So let's start from the coequalizers. Assume that we have a pair like this in the opposite category, and then it has a coequalizer because the coequalizer in the opposite category is just an equalizer in the initial category. So in the category E, it corresponds to equalizer like this. Since this is a reflexive pair, we have a section which goes from A to B. So this is somewhat counterintuitive, but I mean, maybe that's bad notation, but this is a pair in E op, and the section is written in E. So this section satisfies the following. Satisfies the following the following Well, now it tripped me up. Should have used a better notation. Well, it doesn't matter. It satisfies some kind of this relation. And we know from this that G and H are monomorphisms. So if they admit a section like this, then this means that they are necessarily monomorphisms. Okay. Then we can use this fact to see that if we take a pullback like this, so I'm not sure that it is visible, but we take a pullback like this. Then since we pull back monomorphisms, we once again obtain a monomorphism. Moreover, we obtain precisely the equalizer. That's the definition of the equalizer. So F is also a monomorphism. Okay, so now we can apply Beck's commutativity condition to see that a composite like this is equal to the composite like this. And we also know that a composite like this should be equal to the identity on omega y, once again by the corollary of Beck's commutativity condition. And also it should be equal to this. Okay. Well, yeah. Maybe. Yeah. So this implies that we have a diagram like this. So since this is a split coequalizer, it implies that it is a coequalizer of pH and pg. So actually, the words split coequalizer mean something different from coequalizer, because we can say that a fork is a split coequalizer if it admits sections like this, and then from it we can derive the fact that it is actually a coequalizer. So the condition on existence of such sections is sufficient for the fork to be a coequalizer. So this is what this implication means. So we have a split coequalizer, meaning that we have two sections like this, and this implies that it is a coequalizer of pH and pg. So this means that our functor p preserves coequalizers of reflexive pairs, and now we want to show that it also preserves isomorphisms, and for this we do the following. So first of all, if we have an arbitrary morphism in E, then we can consider the following morphism. So consider the singleton morphism into omega y, the corresponding morphism from omega y to omega x, and then we have a graph of f which corresponds by which is classified by the map from x y to omega, which is composite, which is adjoined to the composite map like this. So we have a graph of the map F, and if PF is equal to PG, this means that graphs of F and G are the same, and this means that F is equal to G. So this means that this means that actually the functor P is faithful, and so it reflects monos and apiomorphisms. And by the characterization of isomorphisms as morphisms which are both api and monomorphic, we derive that the functor P actually preserves isomorphisms. Okay. So I guess I want to finish by stating some possible applications of Paress theorem. So first of all, we obviously derive the fact that any elementary topos is both finitely complete and co-complete. because it can be represented as an algebra over, well, as a category of algebras over a monad, and obviously, if a category was complete, then the category of algebras is also complete. And since the opposite category is equivalent to the category of algebras, then this means that the initial category was co-complete as well. And also we can explicitly construct, well, sort of explicitly, this the quotation marks should be quite large here, because this explicit construction relies heavily on very non-explicit existence of equalizers. But we can construct co-equalizers of arbitrary pairs in an elementary topos. So I will once again just describe the construction and not the actual proof, but it works like this. So we can consider an equalizer of a pair of maps like this, which corresponds to PF and PG. Then we can consider maps from third power of P applied to Y to PY, which corresponds to units of this adjunction, and the same thing for X. And also we can consider a map from P squared Z to P to the third power of Y, which are defined like this. So we basically just applied P square, which is an end functor on the category E. And then we can consider, well, we can consider a similar diagram like this, and then by the universal property of the equalizer like this. So E is an equalizer of this morphism, of this pair of morphisms. Moment, is this what they want to say? Yeah, it is. So one morphism is eta applied to T Z, and the other is the morphism which is just P applied to R. We take the equalizer of this pair, then we use the universal property of the equalizer to find a factorization Q like this, and it can be shown that this factorization, it's just a sort of a diagram chase, that this Q is actually a co-equalizer of this pair of morphisms. Which means that we can sort of explicitly construct co-equalizers in an arbitrary elementary topos. Okay. So well, I mean, maybe this construction is somewhat useful because it's easier to construct, for example, limits of sheaves, because limits of sheaves are the same as limits of pre-sheaves, unlike colimits. And then we can sort of apply this construction to, for example, compute co-limits, well, at least co-equalizers of maps of pre-sheaves, which is of maps of sheaves, which is somewhat useful because, as I said, to construct a co-limit of sheaves in general, we need to take a co-limit of pre-sheaves, and we need to sheafify it. And this can be, I guess, somewhat less explicit than this construction. But to be honest, it's quite an explicit itself because it relies heavily on well, on first of all taking equalizers, and second on taking power objects, which is in itself not very explicit. Okay, but still it is a direct application of Perez theorem, and it demonstrates that we can construct co-equalizers using equalizers in a topos. Okay, thank you for listening to this, and I hope that next time we will be able to discuss cohomology and homological algebra in general for arbitrary topoi, and in particular for, well, we will do it in the category of abelian objects in the topos. Okay, let me stop the recording.